Assalamu alaikum wa rahmatullahi wa barakatuh. This is the third part of the second chapter, Linear Momentum. At the end of this video, you are going to be able to verify the law of conservation of linear momentum. But first, let's remember what we took in parts 1 and 2 in this lesson. We defined the linear momentum as p vector equals to mv. We talked about the linear momentum of a system of particles to be p of the center of mass equals to the p of the system. The general expression of Newton's second law is the sum of forces equals to dp by dt, and the theorem of center of mass is sum of F external equals to the mass times the acceleration of the center of mass. The last idea, which is important in our study, the linear momentum of an isolated system is conserved, then the linear momentum initially of the system equals to the linear momentum finally of the system. You should have watched the previous video about verifying the conservation of linear momentum experimentally. In this part, we are going to re-explain the method in our way. First, we need a horizontal airtable with its accessories, two pucks of respective masses MA and MB, two rings each equipped with a steel web connected to it by means of springs. We push the two pucks initially placed on the horizontal airtable towards each other with non-collinear velocities. The pucks slide on the surface almost without any friction. While the puck is moving, we press a spark timer adjusted at a frequency f. Each spark produces a dot on the experiment paper, thus we can study the motion of both pucks. For making the experimental study, we are going to spot the light on the analytical proof, starting from defining the system that we are studying, which is the two pucks and elastic rings. What are the external forces acting on this system? We have the weight of the system, which is MA plus MBG, and the normal reaction. What are the directions of these forces? Weight is vertically downward, where N is vertically upwards. What's the result then? If we add these two forces, then the answer is zero vector, so the system is isolated. Then the linear momentum of the system before collision is equal to the linear momentum of the system after collision. Be careful that these steps are important to you in solving some problems. Now experimentally. First, let's go back to the figure obtained by the experiment. We should name the dots to make the study of the positions be clear, as A1, A2 till A6 or B1 till B6 are the successive positions of the center of mass of A and B before collision, while A6 to A11, B6 to B11 are the successive positions of the center of mass of A and B after collision. We are going to make the study of the system A and B before and after collision. The motion of each puck is uniform before and after collision, since we can see that equal distances are covered during equal intervals of time tau, where tau is constant time interval between each two successive positions. The speed of each puck is determined graphically using the methods of grade 10. We used to divide the average distance between A0, A2 by 2 taus. Or even better than this, we divided the total distance A0, A6 by 6 taus to reduce the possible error in measurements. Anyways, the speed of A before the collision will be constant, and the speed of B before collision will be constant too. After collision, the speed of A will be constant and the speed of B will be constant, confirming the motion is uniform. Knowing that the speed is constant, does it mean necessarily that the velocity is constant? Of course not. Then, what are the conditions the velocity as a vector should verify to be considered constant? Perfect. It is considered constant when it conserves same magnitude and same direction. Then, is the velocity of A constant before collision? Is it constant for B also before collision? After collision, is the velocity is constant for A or even for B? Yes, it is. What is the purpose then? We can then calculate the linear momentum of each puck as PA before as a vector equals to MA VA vector, which is a constant vector. PB before equals to MB VB vector equals to also constant vector. PA after equals to MA VA after as a vector, it is constant vector. PB after also as a vector equals to MB VB after as a vector equals to a constant vector. So all these linear momenta are constant vectors since the velocity for each is constant. But focusing on comparing the linear momentum of the system before and after collision, we will calculate the linear momentum of the system as the sum of the linear momentum of A before and of B before collision. Then the linear momentum of the system will be constant too, and the motion of the system is uniform. Likewise, for the system after collision, it is the sum of linear momentum of A and the linear momentum of B, which is constant vector, and the motion of the system is uniform. The question then is, are they equal? To find the answer, we use the first method. We're going to join the center of mass of each couple AI, BI, and we're going to find that they form a straight line and the distances between successive positions are equal, thus representing a uniform rectilinear motion of the center of mass, so the vector Vg is constant vector, where Vg is the velocity of the center of mass of the system. Therefore, the linear momentum of the system, which is equal to ma plus mb times the velocity vector of g, the center of mass of the system, is also constant through the motion before and after collision. As a result, the linear momentum of the whole system, which is the linear momentum of the center of mass, is constant. Then, linear momentum is conserved. This is a method. But if we don't know the line joining the center of mass, can this be verified? The answer is yes. Let's try to make the study. Remember that the linear momentum of A and B are vector quantities, and they are non-collinear vectors. Hence, we should represent their vectors considering a scale. Measuring the linear momentum of the system before collision means adding vectors. We represent the vectors of linear momentum of A and that of B before collision and after collision, then add them as vectors. So we find that the two measured vectors before and after collision have same magnitude and same direction. Thus, the linear momentum is conserved. Note that you can represent the two vectors anywhere in the region and you are not restricted with this line, and the vectors will be clearly parallel to each other. This is the end of the method of verification of the conservation of linear momentum. You should study the main ideas of the lesson we have taken till now. If you have any unclear step, don't hesitate to ask. Good luck.